Hello, my dear friends, and now we are going to learn about the capacitors. So, what are the capacitors? Well, imagine that there are the dams. Well, same thing. Okay, so what I mean with that, let me explain that first. Imagine that you have a pipe. Yes, again, the pipe. That's the simplest thing I can draw. Okay, so this is the pipe coming from somewhere and the water is flowing out through this, so let's draw some water so that it feels like original. Okay, now the water is flowing out and you are moving something, maybe like fan or something or turbine or whatever kind of thing you are moving. So that's the simple concept. Okay, now imagine that this pipe's water is somehow irregular. Means one time it is coming in 5 layers and then it is coming in 2 layers or slowed down. Like here I have tried to draw this already actually, so this much, and then again the water is coming from full speed. So in this kind of the scenario, the flow will going to be irregular. Flow will be irregular. One time the fan will move faster and another time fan will move slower because of the low pressure and high pressure. So this was the problem of our tap where the water is not coming smoothly. So what can be the possible solution for that? Here the concept is coming. Now imagine that same pipe, but this time something like this happen. Let me make that clearly, and till that point I dare you to imagine that what are the possible things that we can do here. Okay, so I'm just drawing that. Just try to focus upon that and you will get the idea for sure. Drawing this fan, and let's now change the color. Everything will not be the same. Now this flow will gonna fill it up, and let's make it fill it up, and that will going to move the fan. So this is the entire concept, and now the fan speed will not going to change. It will have regular flow output, no matter we have variable input. So in both the cases we are having variable inputs in the term of voltage and specifically current. I meant with that flow word, current, that I showed in some form of water. But if we have a container that we are calling capacitor, that is having capacity to store the charge Q. Well, Q is related to I, as we know, so we are taking the charge, and surely it will maintain a voltage or potential difference that it will going to develop. We are going to discuss that in a while, but let's understand the capacitor, the word capacitor itself first. So first the tank is going to fill up, and then because of the pressure of the tank the fan is moving. So no matter if the flow of the input is high or low, to maintain the continuity we have filled it first and then throwing it out. So if we maintain that smartly, our fan will move with smooth flow and regular flow. So this is the whole concept of the capacitor. I hope you have got the entire idea about the capacitor itself. So when you add a capacitor, or sometimes called as condenser in so many places, so what actually happens if you notice it with the mind of your engineering technological, okay, mind of an engineer. So if you on the fan, it will get start moving or rotating instantly when you are not using the capacitors. But when you are using the capacitor, it will going to take a little movement to start, little extra movement, maybe few nanoseconds extra. Sometimes we are not even able to notice that, but it will going to take that much time extra to start, because first our tank has to fill up. Like in first case we have the wire and the fan directly connected, two wires, two fan, one fan. Okay, now in this case we have a fan connected to the capacitor, connected to the electrical source that we have. So first the tank will get filled up, and then it will allow the smooth flow, and that smooth flow seems faster. Obviously it will seem faster, because if you are starting it again and again from the 0 point, it will be slower and less efficient. So to make it more efficient, capacitors were born. Well, capacitors are not just today's thing. It was some around 200 years ago. Well, a little more than that actually. In the 1700s, late 1700s, they were using the capacitors. Well, that's insane sometimes feels like, but that's the reality. Okay, now let's understand some mathematics of the capacitors that we have to study. So the fundamental equation for the capacitor is charge is directly proportional to voltage or potential, we can say. So Q is directly proportional to V. As much as charge you store in the tank, that much potential or that much energy it stores. Well, that's simple. Now, removing that proportionality sign, we use the C, the symbol C, and that C is for the capacitance. C is capacitance. Capacitance, you can imagine that as the capacity of the capacitor, like small tank or big tank and V-shaped tank, that all the things. So this is the capacitance. This is the fundamental formula, just like the Ohm's law we have seen, V is equal to IR. In here we have seen the Ohm's law, and now we are on fast forward mode. We are on here. So unit for the C is Faraday. F-A-R-D-A-Y. Faraday. Faraday is the unit for the capacitance. C, as we know, it's the coulomb. So we just write simply C, and voltage we write V for the voltage. So these are the units. Okay. Now we also write the capital F, and that's good enough for that. Alright. Now what else we have here? Well, there are several things that we need to study in the capacitor, like we have studied in the resistance itself. That is energy stored in a capacitor that we are going to see, and the series parallel connection that we are going to see that. So let's see one after another. So as you already saw that this is the symbol for the capacitor, and let's add it to the 10-volt battery, let's say, and this, let's say this is 2 Faraday and this is 3 Faraday. So as you know, this is the series connection that we have connected, and now it's time for the parallel connection. So in the parallel connection we just have to do these things and then just add with these battery. Okay, always remember that together series and parallel are also possible, but I have not shown you that. I am assuming that if you go deeper into this subject, you will surely understand that and can figure it out very easily. Okay, so this is parallel connection. We are learning the simplest aspect so that we can understand the things that what actually happens inside the machine. Remember, we are digital logic engineers or digital electronics engineers. So we are learning this electronics, the whole idea of the electronics, just to make a logical concept out of it, so that when we work with our digital designs, that will going to help us in understanding in the deeper level when we work with integrated circuits and all that such complex topics. Okay, with all that said, let's now calculate that. So for the series one, that thing is written as this way: 1 by 2 plus 1 by 3. Exactly, this is exactly like resistance paddler, but this way it is for the series. So 6 and 5, and then as we know, C net or C series is equals to 6 by 5, that is 1.2. 1.2 Faraday is the total or the equivalent of these two. All right, now let's do it for parallel. In the parallel one, yes, you have guessed it right. It is same as the series, so C1 C2 type thing. Well, here I have not written it, so let me write that 1 by C1 plus 1 by C2 and all that. You can take it similarly. Now for the C net, here we just need to add 2 plus 3, which is equivalent to 5 Faraday. So in the case of parallel, we have what? More capacitance. Yes, more capacitance. And in this one, we have less capacitance. Well, that is logically true either. Imagine that you have two dams at one place that will act as one dam itself, right? One container itself. One container is unfilled and then fill another container and then it will going to flow to the load resistance or fan or something that we are using. But in this case both will flow, so the speed will be high, and our load resistance or fan whatever we have will move more fastly. So this is faster. So how can faster be possible? When there is more capacitance. More capacitance, as we see, 5 Faraday is coming, and in this case less is coming, so 1.2 Faraday, because we are wasting time just taking one container's water into another container's water and then we are going to flow it up. So this is just kind of the waste of this process. This entire process is the waste of the time. So actually not waste of the time, it is done purposely sometimes so that we can make our connections working. Well, that's the deeper part of the electronics, but for now we have understood that which one is good for us. So when you are doing something household thing, so we will prefer our series. No, parallel connection. Exactly. So parallel word is a favorite word, I guess, for the people. That's why parallel resistance, parallel capacitance is used to get the more power and less resistance. Okay, finally we are going to study that what is energy stored in the capacitor. How do we find that how much energy is stored in the capacitor? Energy stored in or inside the capacitor. Well, you can simply write the energy either. I'm writing these very big thing in the form of E. So that is half CV square. That's it. C is the capacitance, V is the voltage, and 2 as we divided. That's it. That's all the thing that we need require. Well, if you love derivation type things, so let me tell you a very simple derivation for that. E is equals to Q times dV and Q is equal to CV, as we know. So in the next line we are going to write CV and dV, and in place of that C is the constant, we take it outside, V dV, and on integrating we are going to get simply CV square divided by 2, that we are writing as half CV square. Well, if you don't know much about the integration or not interested in this one, you can just work out with this one. This is okay either. I'm done this so that the people who are interested in maths thing, well, if you are the engineer, you must be interested in a little bit of maths. That is for sure. So this is a little bit of the integration thing that everyone should learn, and this is the way we calculated the energy stored in the capacitor. Well, I don't told you the deeper logic of this, because if you know the integration you can assume that how we are doing it. So okay for this one. Okay, so this is the energy stored in the capacitor. We have studied the network of the series and parallel, and why I left this much space, so surely we need to study something else either. So capacitance is an interesting concept, right? Well, right on. You said correctly, but we don't understand that why you are teaching this all things. We need to go to one last topic, which is inductor itself. So, what the inductor actually do? You make some shape like this. So, it is here. We have seen that. You cannot hide it. This is inductor. So teach us this one. Okay. So we're going to learn this one, and I'm not going to bore you with the capacitor topic insanely long. Well, it can be insanely long, but I am not going to take you into that things. For the simplest of the thing, let me tell you one thing, one last thing. I promise that will not go bigger. Parallel plate capacitor, that is the simplest form of the capacitance design. Well, you may have seen the cylindrical shaped capacitor, there are the parallel plate capacitor, there are spherical shaped capacitor. Well, any kind of the shape is possible. This one is majorly seen all the places in electronics. So this is most efficient one, you can say, for our purpose. Well, but I'm telling you this one because this is very basic. So this is the distance between them, and this gets positively charged, and that is going to get negatively charged, and it will going to draw electric field. Well, if you have studied the electricity, you will surely able to connect that. If you have not, just go with the flow. So this is the electric field, and the dipole is here, as the positive negative charge has got separated. So we have positive and negative charge separation here, and because of the positive negative charge separation, now what we are going to do is to find the E total, which will going to give us the E of the positive part and E of the negative part. Ultimately, I am not going to solve everything, but I gave you the entire idea. If you have learned the electric field, you will surely able to connect that, or if you have any doubt, you can surely ask that too. Okay, so the entire idea of it is the capacitance, the value of the capacitance becomes epsilon naught A divided by D. Well, what is A? A is the area here. So A is the area, that how much area we are having, and D is the distance between them. One, what is the epsilon naught type thing here that we can see? Well, epsilon naught is permittivity of free space. Permittivity of free space. Well, this is the property of the space in simple words, and this is a constant. So we are having a constant value here, and A is a variable that we can change. We can change the area, we can change the distance between two plates. So this is all about the parallel plate capacitor. You can make a parallel plate capacitor very simply by using this simple formula, and can calculate what is gonna be the capacitance of it. Well, we can make other such formulas either. Just the area will going to change, the distance will going to change. We might able to put something inside and separate this capacitor in two equal pieces, four equal pieces, change the design and all that. If you have that kind of the question, I am liking you already because that questions are little bit higher level. So we are going to learn that. Well, if you have gone through the high school physics very goodly, you surely know this already. But if not, that's not worry about thing. We will learn that later. But for now, this is all about the capacitance. So why I told you these all the things? Well, the reason is to bring out the curiosity in you, so that you are a engineer. You are learning the engineering subject. This is digital electronic engineering, so you must be curious. Even if you don't know the entire concept, that must spark in your mind, and that spark will going to lead you to the next level of your learning. So in the next one, we are going to learn about the inductor. So take care and God bless.